Okay, so before I talk about smart pointers, I would like to discuss C and C++ style memory management, just some review so that we can kind of compare the advantages and disadvantages once we talk about smart pointers. Okay, so the example code on this slide, is showing a example struct called foo, and in main we are creating a new instance of that struct. We are invoking malloc, giving it the size of the memory that we need in bytes. So we give it the size of operator for foo, which will give us the size in bytes that foo takes up. And then malloc goes off and allocates that memory. It will return a void star pointing to that memory, so we have to cast it to a pointer type for our object. So then we have some calculation or operation involving our object, and then once we're no longer using it, we have to invoke free and mark that memory as unused. If we do not invoke free, if we don't free the memory, then we have a memory leak. And memory leaks are very undesirable because if you have memory leaks going on, for example, in a loop, or if you have a lot of allocations going on, a lot of memory that you need, and you're not freeing it, then you could potentially actually run out of memory at some point, which is very bad, and it would cause your program to crash. So, in C++, we have new and delete operators. So instead of invoking malloc, we used new and delete for free. So when we need to create a new instance of an object, we just say new and then the name of that object. And if we need an array, then we give it a array subscript with the size of the array in there. So new and delete is an improvement over malloc and free, at least I think, because for one thing, malloc always requires the size of memory that you'd like to allocate in bytes. New will automatically deduce the size of memory that you need based on the size of the class. The compiler always knows anyway the size of the class, so it can just deduce that for you. You also don't have to cast it from a void star to a pointer type. New will always have the pointer type of your object, and that's because new is an implicit member function or member operator of every class. It is not a universal thing. So we also have some, operation here involving our class, and then we invoke delete, and delete will free that memory for us. So we still have to manually free that memory. It's still very much unlike a stack variable in that we have to free it when we are no longer using it. So still the potential exists for leaks here. Alright, so now let's talk about the meat of the video. Let's talk about smart pointers. So the first kind of smart pointer that we're going to talk about is unique pointer. Okay, so unique pointer enables you to have unique ownership of an object that you allocate, and when the unique pointer is created, that object is allocated, and then when the unique pointer goes out of scope, when it is destroyed, its destructor will destroy the owned object. Okay, so this is incredibly powerful. Let's look at the example code here. So here we're creating a unique pointer. Okay, we use std_make_unique, which is a helper function that forwards the arguments that you give it using std_forward. It forwards those arguments to the constructor of the class. Okay, and you can use unique pointers constructor directly, and but unique pointers constructor requires a pointer, which you get from invoking new. So you use unique pointer just like you use a regular pointer. You can use the arrow operator, okay, to access member variables and member functions. And then, down here at the end of main, our unique pointer will go out of scope. Okay, so its destructor will be invoked, and the unique pointer's destructor will destroy the owned object for us. So we don't have to, in this case, manually free the memory. Unique pointer will handle freeing the memory for us. So it's a lot less likely that we're going to forget to free that memory. So this is leak resistant, as I say. It is not totally invulnerable to leaks, as we will talk about later. It is leak resistant. You can still have situations where there are leaks with unique pointer and shared pointer, but these situations are rare. So one of the big things about unique pointer is that you cannot assign it or copy it. So its copy constructors and assignment operators are actually deleted. So you cannot use them. You cannot copy a unique pointer. That's why it's called unique pointer. But thanks to move semantics, you can actually transfer ownership of that unique pointer across scopes. So here we see an example of that in action. So we are creating a new unique pointer here at the beginning of main. So after this make unique, main has ownership of the foo object. Okay, it's in the scope of main. So then we call sum fn, okay, and we give it the unique pointer that we created up here, okay? Excuse me. So we give it the unique pointer that we just created, but we cannot give it that unique pointer directly, because then it would try to copy construct arg with that unique pointer. And the copy constructor of unique pointer is deleted, so that would give us a compiler error. So what we can do, however, is we can call stdmove, and stdmove will turn f into an r value, which will then select the move constructor of unique pointer, and that will move construct arg using f. So f will actually be invalidated. It will no longer be valid after the call to sum fn. Okay, but during sum fn, arg will have ownership of the foo object that we created in main. So we essentially transferred ownership, and we now have access to that object that we allocated in main, but we would like to use in sum fn. So if you have a lot of situations where you need to use objects outside of your scope, the scope that they're allocated in, then maybe that's a good sign that you don't want unique pointer, but rather that you want shared pointer. So shared pointer is great for objects that you would like to use in more than one context, okay? So shared pointer, what it does is it implements reference counting. So what reference counting is on creation, on creation of an object, you have one reference to that object, okay? So, for example, down here we're creating a new shared pointer, okay? So after we create that shared pointer, one copy of a shared pointer exists owning that particular object. So references to that object, we have one reference to that object, okay? So now we call sum fn. It's just like the code on the previous slide. We give it f. So arg is copy constructed with f. We don't use stdmove here. The copy constructor of shared pointer is not deleted. It's perfectly fine to copy them. When you do copy a shared pointer, it increments the number of tracked references. So at the beginning of sum fn also has ownership of the foo. Main also has ownership of the foo. So they both have ownership of the foo at this point, okay? At this point in time. And so at the beginning of sum fn, the number of references is 2. At the end of sum fn scope, we decrement the references, okay, because arg is actually destroyed at the end of sum fn's scope. So the destructor of that shared pointer will decrement the references. So then, after the call to sum fn in main still has ownership of that foo object. So f is not invalid, it is perfectly valid. But once we reach the end of main's scope, okay, down here, then f's destructor is invoked, which decrements the tracked references, and excuse me. So it will decrement that reference counter, and then only when the number of references is 0 is that object destroyed. Okay, so at the end of main, that object is still destroyed, and everything works out. We were able to use the object in multiple contexts, okay, and it was just great, okay. So, like I said earlier, smart pointers are leak resistant. They are not invulnerable to leaks. You have to be smart for smart pointers to be smart, okay? So, a little bit of a misnomer, but anyways. If you use them properly, you will not have problems. So the example code on this slide actually shows a situation where smart pointers will cause a leak, okay? And this is kind of interesting. So what we have here is we have a struct called person, and every person has a friend, right? I tried to call this member variable friend, but I realized that's a keyword, so I actually cannot do that. So I called it amigo. So everyone has an amigo, right? So in main, we construct two people, Joe and Bob, okay? And we make shared pointers to those people. So we have a shared pointer to Joe and a shared pointer to Bob. So when we assign a shared pointer, it increments the reference counter, okay? So we say that Joe, his amigo is Bob, okay? So references to Bob is incremented, and now there's two references to Bob. We set Bob's amigo to Joe, okay, and now references to Joe is 2. So now what happens when we go out of scope in main, okay? So when Joe and Bob go out of scope in main, these shared pointers are destroyed. Their destructors will decrement the references. And now the counted number of references is 1. So that's not 0. So shared pointer will not destroy those owned objects. So if you were to actually write this out and compile it and maybe have some debugging output going on in the constructor and destructor of person, you would actually see that the destructors do not get invoked for this code. So there is a leak here. There is a leak going on. So how do we fix this situation? This is called circular referencing, and it's a pretty common problem. So circular referencing, we break circular referencing by using weak pointer. So weak pointer is a non-owning reference, okay? It is, it references something that is owned by one or more shared pointers, okay? But it does not itself indicate ownership, so it does not affect the reference counting, okay? So this is exactly the same as the code before, except instead of amigo being a shared pointer, amigo is a weak pointer, so it will not affect the reference counting. So we create Joe and Bob, shared pointers to person objects, and then we assign Bob to, so we say that Joe's amigo is Bob. So references to Bob, where it was previously incremented there, it is no longer incremented because weak pointer will not affect the reference counting. And similarly, when we set Bob's amigo to Joe, references to Joe does not increase. So then when we go out of scope in main, okay, references is decremented because Joe and Bob, those shared pointers are both destroyed, and when they're destroyed they will decrement the references, and so references will be 0 at that point, so both will be destroyed.